There are lots of situations where we might have more than one object in a system that we're going to try and use Newton's laws to analyze. For example, we might have a trailer being pulled by a car, or we might have another example might be, say, a box in the back of a truck. And in cases like this, where we have two objects moving and their motion is related in some fashion, or even if they're not moving, if we have, say, a mass hanging from below another mass, where they're not moving, but the forces on the system really depend on how the system is arranged, then we call these coupled systems. And there's some basic ideas to understand to help you analyze them. There are lots of different ways in which we might have two systems connected. And I've just broken them up into sort of three general categories. There's when we just have two objects touching. This might be in the case of the stacked boxes, which is an example we've been through before. The two boxes touching each other, which we've been through before. This could be the case of stacked boxes, where maybe one box has there's friction between one box and the other box. This also would be the case of the box in the back of the truck. And so you can see how this general idea of two objects touching and forces on them could be turned into lots of different situations. The next sort of general class I've given things is when you have two objects that are connected, usually by a rope, but possibly by a drawbar, by a beam, something that allows them to pull, something that we're probably going to put in tension. And knowing how to break up our system into different masses with pieces that are in tension is really important. And then the last sort of class of problems that we're going to see are what I'm just going to call pulley problems. This is where I have a mass and another mass connected by a pulley, and it can look like this, or we've seen one, for example, in lab where it looks like this. You're on an incline with a mass hanging down, or another one where you had a mass on the table coming over a pulley with a mass hanging down. There are lots of different ways we could arrange this. We could have people pulling down instead. You could have more than one pulley. There's lots and lots of different iterations we could have for these kinds of pulley problems. So these are just three basic classifications for the different types of coupled systems that we can have. These aren't, this is not by any means a complete classification, but it's just the three general classes that you see most often in this introductory class. I'd like to briefly go through each type of coupled system and maybe give you some tips and tricks on how to approach these kinds of things. With these boxes or objects that are touching, and remember, this could be a box on the back of a truck or something like that. Who knows what it is? One of the key ideas is to define our system. We might define our system as both boxes together. This is often common when we see that both boxes are going to have the same acceleration. And if that's the case, then we might define both boxes together, and we can see then that we've got this pushing force, and we've got a normal force from the ground, and we've got the force of gravity, which is going to be the sum of the two masses times gravity. All right. Maybe that's when we see they're both accelerating together. And then after that, then we might divide this up into different systems. Maybe we'll have a top box be a system and the bottom box be a system. And we just do this dividing up of systems as many times as we need to, especially if we're trying to find, say, what are the forces between boxes. So that's just one idea that you can use when you have two objects touching. And it's going to be really critical because, as we've already seen in one example, there may be forces that are exerted on one system that are not present on the other system. For example, this force that's pushing is not being exerted on this second system, which is just the big box. Okay, so it's very critical that we define our system and ask what's touching it, because remember, only things that touch can exert forces unless they are gravity. Unless it's gravity. Gravity is our one long-range force. But other than that, hopefully that gives you some keys to, or some ideas on how to analyze these kinds of systems where you just have two objects touching, especially if they have the same acceleration. We can define them individually by boxes or the whole thing together to get our acceleration. In the cases where we have two connected objects, typically this connection is going to be by some sort of rope, but it might be by some sort of bar, something generally where we have a tension force between our two objects. We're going to do the same thing we did before, where it's going to be critical that we define our system. And we may, especially if they're moving together, we may want to do the same trick of defining the whole thing as our system to get some sort of acceleration, because we will always deal with strings that cannot stretch. And so the distance between our objects has to be a constant. And so the acceleration has to end up being constant for the two objects. This is just typical. And so often we can define the whole thing as our system. And then if we wanted to know the tension itself, we might define the system, our individual objects as a system. One thing that becomes really important is to realize that this force of tension may not be the same as our pulling force. Or even if we're not accelerating, if you look at the case where we have, say, two people hanging or two masses hanging connected by a rope, the tension in this lower part, maybe we call that the force of tension, let's call that the force of tension 2, isn't going to necessarily be the same as the force of tension in this upper part. Force of tension 1 is not necessarily the same as force of tension 2. Now that should be a little bit different from what you've seen before, because usually when we've had strings connecting things, then the force of tension in any part is always the same. But when we add something in between, when we put a mass in between, then suddenly this is no longer true. This tension and this tension are not necessarily the same. And so that's one key idea. You just have to then, and it's really straightforward, then we just have to define our systems. Again, for example, in this hanging person system, we might define our lower person as a system and our upper person as a system, and use that to get the tension in the top and the tension in the bottom, just with the understanding that they're not necessarily going to be the same. So a lot of the techniques are very similar, with just now we are being connected by ropes or bars or other things, and we have to be careful about making our tensions the same in different places, especially when there is some sort of mass, something in between the two parts of our rope. And this last type, the pulley problem, really deserves to be a class all on its own, because anytime we introduce a pulley, the point of a pulley is that it redirects a force. So if we had a force pulling downwards on this side, then as it goes around the pulley, it's going to pull up on this side. All right, so it's really just a way the pulley acts to redirect the force. Now this is, and we'll start out with this is typically going to be true of massless pulleys. And later on, when we learn about rotation and rotational inertia, we can actually add mass to the pulley, and then it does some interesting things. But at least to start off, we'll start off with massless pulleys, and then the point of the pulley is that it redirects my force around the pulley. one of the really important things that force redirection means is that if I tried to, say, define both masses as my system, in spite of the fact that these are still connected by a string, and so the distance, this around the pulley distance, has to stay the same, and each of these will have the same magnitude of acceleration. If I try to define the whole system as my, or both masses as my system, I run into trouble because the center of my system is moving. As one mass goes up, maybe, and the other mass goes down. So we have to be a little bit more careful. We actually can't use both masses as our system. But that's okay. We know how to deal with that. We just have an acceleration maybe of this one upwards, an acceleration for this one going downwards, and then we just define a system 1 and a system 2. And from there, we can solve our system. Now, as long as our pulley is massless, then we don't have to worry about this idea of different tensions being in different locations in our string. Remember, that was only if we put mass in the middle, but we don't have mass in the middle. So for this case, we're going to have the tension on this side of our string be the same as the force of tension on this side of our pulley. So the force of tension on both sides of the pulleys would be the same. If we, say, hung a mass down here at the end of one, well, then this force of tension would be something else, not the same. But as long as we're going around the pulley and there's no mass here, then the force of tension on one side of the pulley and the force of tension on the other side of the pulley stays the same. And so that gives you some ideas to on how to address these different situations. I'll put a link to a video that shows you pulleys and walks you through with some real examples of how pulleys work. And then hopefully in class, and maybe with some other videos, we can show you how to solve these pulley problems, as well as the other coupled system problems that you might encounter.